Welcome back to Deep Learning with the Wolf. I'm very excited to have a special guest with me today. So please introduce yourself.
Thank you, Diana, for having me. So, I am Shubham Sharma, founder of SunitechAI, which is an AI powered tech platform. So, a bit about me, I did my bachelor's back in India in petroleum engineering. And then I got the opportunity to work for one of the largest oil and gas service company, which is based out of US, which is Baker Hughes. And that's where I got my first tryst with data science, and that really intrigued me. So I decided to come to the US, did my master's from sunny Buffalo, New York, and now I am working with UPenn. And I do research at UPenn, and I am also building this side project, which is my startup Sonatech AI, where I share my expertise on data science and generative AI with professionals, with students, as well as I do offer consulting services for companies as well.
So, just a fun side note, we studied in the same corner of New York because I went to SUNY Geneseo, so not far from you.
Oh, great.
So, the reason why I wanted to have you on is you had a very interesting paper come out recently. So, I thought maybe you could explain it in your own words and break it down for audiences. So let's start with the big picture. What is this paper about in your own words?
Sure. So the paper is titled as GMC. We are calling it as Geometric Mixture Classifiers, right? And me, along with my co-author Prashant, found out while working on various classification problems that there is actually no single classifier which can deal with multi-model problems very efficiently. And most real-world categories are multi-model. A single class would often occupy multiple disjoint regions in the feature space. You can take example of medical diagnosis, you can take example of fraud detection. Multimodality is there in almost every single real world use case. And that's where we experimented with implementing a mixture of hyperplanes to do the categorization, and the GMC algorithm was born.
So most classifiers use one rule per class, but your model uses several. So why does that matter?
Yeah, so the limitations with other models is, let's talk about linear models. So classical linear models like logistic regression or linear SVM, they would use one global hyperplane per class. So as I said, real world data sets are scattered. They have multi-model class structures. So these type of methods would struggle with scattered class structures. Then there are high capacity alternatives, which are sort of non-linear models. We can talk of kernel SVMs, deep networks, which can be used for doing non-linear classification. But then they sacrifice interpretability. They would often require heavy tuning, and not to mention they would incur significant computational costs as well. The existing approaches force this trade-off that linear models would lack expressivity, and the kernel methods and more non-linear models would add the complexity plus the cost, and deep models would obscure the decision geometry. So this is the threefold challenge which we are trying to solve using geometric mixture classifiers, right? So our model is uh, that can handle multi-model structure without any heavy black box architecture. Two, it would be data and compute efficient. And three, it would provide geometric interpretability. So you can actually explain how decisions are being made, why the model is giving a certain prediction for a certain observation can be explained relatively better as compared to the other alternatives.
So if you had to explain GMC using a real world metaphor, say in a classroom or in a city, how would you describe what's going on?
So to explain it very simply, the GMC model is an ensemble technique. We are proposing it as a mixture of hyperplanes. So that's what solves this threefold problem. For example, let's say if we take the use case of healthcare and medical diagnosis. So we have diseases where symptoms or features can be present in distinct and multi-model clusters. right? For example, subtypes of cancers, which are identifiable by different test patterns. And being able to identify these clusters is not as straightforward as it seems like. Specifically, the linear models struggle, and the non-linear models, the more complex ones, as I explained, would do well. But then there are other challenges in terms of computational complexity, in terms of explainability, right? So what we are doing is we are modeling each class as a mixture of multiple linear hyperplanes, and think of these linear hyperplanes as experts. So rather than one single global hyperplane, we are proposing it to be modeled as a mixture of multiple linear hyperplanes. So that's what makes the main difference, that makes it relatively computationally efficient as well as explainable at the same time.
So if someone wanted to build with this model today, is it ready? Is the code available?
Yes, the code is part of the a paper that is published. In the paper, you can find the GitHub repo where all the code is available with all the data sets on which it has already been tried, and on the results are also available on the GitHub repo as well.
So finally, what is next for you?
Yeah, so I mean, the main reason why we published this paper, and why I wanted to come on this interview and talk more about it, so as to showcase this to the research community and look forward to the research community for active adoption of the algorithm and extension of the algorithm. Possibly, we do have mentioned several avenues where the model can be improved, and you know the other data modalities where it can be tried. For example, for now, the algorithm demonstrates that it is possible to build classifiers which are both accurate and intrinsically explainable. But the way the algorithm is basically doing it is combining the clarity of linear models with the expressiveness of non-linear baselines. What we would look forward from the research community is to extend the idea and explore it with other data modalities, with more complex data sets, and identify such cases where its regularization or other components can be improved to fit the needs of more complex data sets.
So what's one idea from this paper you hope listeners walk away with today?
So the core idea of the paper is it is possible to build classifiers which are both accurate and intrinsically explainable, right? So basically, GMC is able to point toward a middle ground where neither accuracy nor transparency needs to be sacrificed. And that's the main idea, we want the readers to take away from this paper. I mean, generally in machine learning, there's this common notion that there is a trade-off between interpretability and performance. But what we are trying to address through this algorithm is to solve for this problem, a very long-standing problem, and potentially make interpretable AI more practical and appealing to the industry.
Excellent. That's all the questions that I had, and you explained that so well, breaking it down for me. I have such a greater understanding of your paper now. So is there anything else that you would like to add before we close?
Finally, I would express my gratitude to you, Dinah, for taking me up and helping me explain the paper to the wider audience. So thank you very much for this interview. And finally, I would want to close by thanking all the listeners and readers of the blog who would listen to this and potentially take up the challenge of trying out the algorithm to more challenging and diverse data sets.
Excellent. Thank you so much for being on our podcast today.
Thanks a lot, Diana. Thank you very much.